The Big Theta and Big Omega.
I'm Jeremiah Olipas and I will explain the introduction of Big Theta and Big Omega. Big O, Big Omega, and Big Theta are three different time complexity notations for asymptotic analysis. Anytime you run a program, that program is going to take up resources from the computer, which will take up processing time or memory space. The goal of Big O, Big Omega, and Big Theta and asymptotic analysis in general is to analyze how much time a program will take, the performance behavior of an algorithm with regards to an increasing amount of input. So, ang Big O is an upper asymptotic bound for an algorithm. Ito ay malaga sa pag-evaluate ng worst case performance. Samantalang ang Big Omega is a lower asymptotic bound for an algorithm. Mahalaga naman ito sa pag-evaluate ng best case performance sa algorithm. And it is essentially the opposite of Big O. And ang Big Theta is the tight, most accurate asymptotic bound for an algorithm. It isn't an upper bound or lower bound, but it's the bound that matches closest to the behavior of an algorithm. Both an upper bound and lower bound at the same time. In industry, this is the far most commonly used form of asymptotic algorithm analysis.
Common runtimes. Runtimes complexities are generally represented using a mathematical notation or the Big O. It is a great way of representing the upper bound of any function or a procedure, or in this case, the time taken by the algorithm to run. So we generally represent the runtime by a function inside the Big O, like Big O of n, Big O of log of n, and so on. Please note that the function inside the Big O does not represent the number of steps, operations, expressions, or the amount of the time the algorithm will take to run. Rather, in layman terms, it is just an approximate and generalized measure of how the number of operations increase when we increase the input. Big O of 1 is known as constant time. No matter what is the input value and how many inputs or elements are dealt with, the algorithm will always take the same amount of the time to execute. This can be made possible if we are able to find out or derive a formula using which we can calculate the result directly using mathematical computation rather than iterating over the collection of data. Here, the size of n does not impact speed. Next is Big O of log of n. It's known as logarithmic time. Doubling the number of elements, the amount of processing that has to be done does not get doubled. This generally occurs when we compute the result by iterating over only some of the elements in the given collection of data rather than iterating through each of the elements. Here, our runtime change with respect to the log base of n. Big O of n is known as linear time. As the name suggests, this represents a linear relationship. As we double the number of elements or inputs, the amount of processing that needs to be done also increases. This occurs when we need to iterate over each element of a collection of data. A very simple example for this is to add the elements in an array. To do so, we will have to iterate over each element once. We would mean n iterations. Here, our runtime changes directly with respect to n. Big O of n log of n is known as superlinear time. Here, our runtime is slower than linear but not enough to be polynomial. Polynomial time. Here, our runtime has slowed down to being dependent on the seed degree of n. Exponential time. In this case, the addition of a single element in the collection or incrementing input by 1 would cause the amount of processing required to be doubled. If you end up solving a problem with this time complexity, you might want to look back and try to improve the solution. The algorithm having exponential runtime is going to be very slow. Here, our runtime has become proportional to a value c raised to our input size, very slow and explosive. Next is Big O of n factorial. It is known as factorial time. Our runtime is now very slow, being equivalent to the factorial of our input size.
Hello everyone, this is Sheila May Cardona. Big Omega is the least helpful and thus least. This is because the best case of a program is not as impactful on runtime as its worst case. Big Omega is the lower asymptotic bound for an algorithm, useful for evaluating best case performance of an algorithm. It essentially the opposite of Big O. Big Omega shows us the lower bound given a large enough input. Big Omega shows us how fast our algorithm can run. Big Omega is a sort of order notation used to compare two growth functions, runtimes or growth rates. The function is used to describe the performance or complexity of an algorithm. Understanding the math, for a function f of n, we can say that it is big omega g of n, denoted lower bound g of n given the following: k multiplied by g of n less than or equal to f of n. K is a positive number that we multiply g of n by, so it is less than or equal to f of n. N is the inputs for our functions. Note: you will want to choose n such that g of n will eventually be less than or equal to f of n. F of n is our initial function that represents our program's runtime. G of n is a function we are bounding f of n below by and saying g of n, when modified by k, will always be less than or equal to f of n from a point on. The first example of big omega. F of n is equal to 50n cubed plus 20n squared plus 10n log n plus 30n. By dropping the constants, we get f of n is equal to n cubed plus n squared plus n log n plus n. After that, we now say that the lowest order term is n, and this means that f of n is a lower bound of n.
Hi guys, I am Mark Angelo Agron, one of presenter of this topic, example number 2 of Big Omega. In this example, function of n equals 5n squared plus 10n log n plus 2n plus 8 log n. By doing the same process, we get log n as the lowest order term. So we can say that function of n is lower bound of n. To quickly get the big omega of a function of n, one can do similar process to finding big O quickly. The given function of n, the first is drop constants. The second one is to look for the lowest order term. Gaya nga ng example 1 at 2, kung makikita natin ay unang tinanggal ang mga numbers bago ikumpara kung ano ang pinakamababa sa mga term at yun ang nagsisilbing sagot.
Big theta is the tight, most accurate asymptotic bound of an algorithm. It isn't an upper bound or lower bound, but it's the bound that matches closest to the behavior of an algorithm. In other words, it is an exact bound of both upper bound and lower bound at the same time. It is also the most commonly used form of asymptotic algorithm analysis. In understanding the math, we are able to represent the big theta of a function f of n by referring to its big O and big omega values. For f of n to be big theta g of n, denoted exact bound of g of n. F of n must be both upper bound of g of n and lower bound of g of n. K and c are just arbitrary constants we multiply g of n by to obtain these properties. K multiplied by g of n represents the big omega of f of n. C multiplied by g of n represents the big O of f of n.
Since big O and big omega represent upper and lower bound respectively, if both of them can be represented by g of n multiplied by some arbitrary constant, then we know that f of n in between this function. So, on average, f of n will have a runtime that is also g of n. In short, there is no kind of relationship of the type big O is used for worst case, theta for average case. All type of notation can be or sometimes used when talking about best, average, or worst case.
Examples of big theta: f of n is equal to 50n cubed plus 20n squared plus 10n log n plus 30n. Since f of n is shown to be bounded above and below by n cubed, we are able to show how on average it will be n cubed. Example number 2. f of n is equal to 5n log n plus 2n. Since f of n is shown to be bounded above and below by n log n, we are able to show how on average it will be n log n.
I am Rengbel Oreta and I am the 10th presenter of this group. The summary of this topic. The big data is our program's average case running time. While big O and big data refer to two polar opposites, big data is the mean running time of our algorithm. The big data summary I exactly want to say is the big data notation allows us to state both an upper and a lower bound of the growth rate of a function. The big omega shows us the lower bound given a large enough input. Big omega shows us how fast our algorithm can run. Big O allows us to state upper bounds on the growth rate of the function. We want to state a lower bound on a growth rate. We use big omega notation. The definition is almost the same as the big O definition except the direction of the inequality has been reversed.
Example for asymptotic bound. Asymptotic example for lower bound. If you can see, we have here the function t of n is equal to n squared. First we can do is to find the f of n. And here I choose a linear function and choose a c lower bound and multiply it by n. Then it works, but there is an appropriate function for lower bound, which is tighter than linear function, and it is the n log n, because big omega is about a tight lower bound. Next example is the big theta or the exact bound, and here I choose a linear function. We can choose a c upper bound and a lower bound. And to prove that f of n is equal to n, I choose a c upper bound of 100 and c lower bound of 1/2. And here it proves that the function of t of n is equal to linear function. 5 questions. Blank is the tight most accurate symptotic bound for an algorithm. Big theta. Blank is a lower asymptotic bound for an algorithm useful for evaluating best case performance of an algorithm. Big omega. Blank are generally represented using a mathematical notation big O. Runtime complexities. Blank are 3 different time complexity notations for asymptotic analysis: big O, big omega, and big theta. It is represented by big O log of n. Logarithmic runtime. Thank you for listening.